We have just seen how to translate the previous notions of convergence of Borel function to the case of random variables. We saw what does it mean to converge almost surely, to converge in probability, and to converge in LP. We saw a remark that convergence in LP implies convergence of the expectations. And now we're talking about some type of convergence of random variables, which is not really convergence of the random variables themselves, and that's why we did not see this in the previous video lecture, because it's convergence of their distribution. Okay, so this is convergence in distribution. And well, to keep in mind what is a typical case of convergence in distribution, the main examples, well, the king of all the examples is central limit theorem. But we're also going to see that sometimes we have, under certain conditions, we can have sequences of random variables converge to some exponential random variable. And we're not going to see it in this module, but you can have some sequences of random variables converge to Poisson. So, and all these justify why we want to study these distributions, Poisson, exponential, and normal random variables. So what is convergence in distribution? This is the definition. It's not the most natural definition, but this is the one which is, in most cases, the simplest one to check. And it says the following. So random variables x, we say that they converge in distribution. They converge in distribution to another random variable x if their cumulative distribution functions converge to the cumulative distribution function of x at, well, let's say almost every point, or let's be more precise, every point x at which fx is continuous. So we do not require convergence in points where fx is discontinuous, and there is a good reason for that. We're going to see some examples soon that help understand it. And so when this happens, so this is a convergence for every x. So this is a pointwise convergence. We're not making any measurements of distance between these two functions. We're just, for each x fixed, we have this convergence. And for each x, except those where the function is discontinuous. And so let us see some examples. So here's an example of convergence. Suppose we have a sequence of random variables xn. It doesn't really matter if they're independent or not. And in fact, for convergence in distribution, it doesn't even matter if they are defined on the same probability space, because convergence in distribution is about the cumulative distribution function and not about the random variables themselves. So let's assume each one of them is distributed as a geometric with some small parameter Pn. So P indexed by n, and this Pn is going to be taken smaller and smaller. But well, for each n fixed, we have here that this is the cumulative distribution function of the random variable Fn. So this is the cumulative distribution function of a geometric random variable with parameter Pn. And let us assume that Pn is becoming smaller, but it's becoming smaller like this. Take, for instance, Pn equal lambda over n. Well, that is, of course, if this number is smaller than 1, otherwise you can take it anything. It will, as n gets larger, this will become smaller than 1, so you can take this equal to lambda over n. But in fact, you could also even add some small term here, as long as this small term tends to 0 when divided by n. It tends to 0 as n. And then this would still hold. So we have these smaller parameters, and now, of course, these variables will become larger and larger, because a geometric with a small parameter it just means you keep repeating the same experiment again until you get success. And well, if the probability of success is getting smaller, then it takes longer, many and more attempts to get success. So of course, if we want to have any convergence here, we need to divide these random variables by something. Let's divide them by n and check that this converges to an exponential distribution. So this is a very interesting property. So which means geometric with a small parameter, it looks like an exponential if we look at it at the right scale. And well, how can we show that? Well, let's just do the computation. What will be f of xn over n, okay, at some point t. This is the probability that xn over n is at most t, and this is the same as the probability that xn is less than t times n. Well, if we assume t times n is a natural number, then if t times n is a natural number, which means t is a natural number divided by n, okay, then this becomes, we just have to substitute this. This becomes 1 minus Pn, and Pn, we assume Pn is lambda over n to the power Tn. And well, we know what this limit is. This is a classical limit in calculus. This is the exponential limit. So this, we know it converges as n tends to infinity. This converges to 1 minus, so get 1 minus e to the minus, because we have a minus here, lambda, because we have a lambda here, and t, because we have a t here. And this, in this limit, that's the limit exactly when we have 1 over n here inside the parenthesis, and n here in the exponent. So it converges to this number, and this number is exactly equal to the cumulative distribution function of an exponential random variable. So we have this convergence as stated.